Okay, we are live on YouTube and the meeting is getting recorded in the cloud. Welcome to the Silicon Valley chapter of IEEE Computer Society. I am the chapter chair, Vishnu Pendyala. Ours is the largest chapter in the Silicon Valley section of IEEE with over 4,000 subscribers in our mailing list and a strong following of over 12,400 on Twitter alone. We are uniquely positioned by the virtue of our location and available expertise. And today, we are fortunate to have a speaker from Hyderabad, actually, talking on a very important topic, which is democratizing natural language processing, considerations from resources to algorithms. In the recent times, there is an enormous increase in the use of digital media as a channel for communication. This, combined with the fact that natural language is a ubiquitous mode of communication, has increased the volume of natural language data available for processing. Also, this has resulted in opportunities for extending NLP-based services and solutions in multiple languages. All the existing algorithms for NLP tasks have been shown to achieve reasonable performances for the high resource languages such as English, French, and other such languages across tasks. The same is not true for many other languages widely spoken in the world. To ensure that the benefit of NLP research reaches a wider audience across different regions, it is important to pay special focus on the low-resource languages or consider support for low-resource languages in an intelligent manner in the algorithm design phase. So we are fortunate that the speaker for today will address this important topic and will touch upon a few such considerations in this talk. The speaker is Dr. Maunendra. He is an associate professor of computer science and engineering at IIT Hyderabad in India. Currently, he is also serving as the head of the department of the artificial intelligence department at IIT Hyderabad. IITs, we all know, are premier institutions, renowned institutions in the world. Dr. Maunendra received his MTech degree in computer science in engineering in 2006 from IIT Kanpur, and Ph.D. in 2014 from IIT Kharagpur. In the past, he has also worked for Sybase India Private Limited and Samsung Research Institute, Bangalore. His research interests are in the areas of application of machine learning and artificial intelligence in the domains of course, natural language processing, NLP, information retrieval, recommendation systems, and so on. He has published at various reputed venues like ACL, excuse me, NAACL, CIKM, ACM Rexis, ACM UMAP, IEEE, ASO NAM, IEEE Transactions on Computational Social Systems, and so on. He serves as a reviewer and is on the program committee for several conferences and journals like Neurocomputing, IEEE Transactions on Computational Social Systems, IEEE Transactions on Multimedia, IEEE Transactions on Knowledge and Data Engineering, Social Network Analysis and Mining, and more of such prominent journals. More details about his current research and publications can be found on the IIT Hyderabad webpage. Before I turn it over to Dr. Maunendra, I just wanted to point out that you can post your questions on the chat window, either on YouTube or on Zoom, and I will relay them to Dr. Maunendra. Links to the video and slides will be posted on our website in a week, provided the speaker is okay with it, and on IEEE.tv. So let's hear from Dr. Maunendra without much ado. Over to you, Dr. Maunendra.
Thank you, Dr. Vishnu. I also got to know quite a few things about the society, its wide reach and so on, which is really amazing. Thank you. So Mm, Yeah, it's a pleasure to be here and present a part of my work and also some of the things that we regularly discuss, uh, which are the needs of the hour, especially for the natural language processing kind of problems domain. So, yeah, it's a pleasure to be able to give this presentation to this group. Also, one of the reasons why I'm able to give this presentation is that all the attendees here, or people who are watching it on, say, YouTube or other media, is that we know at least one language in common, which in this case is English. So just, I mean, and we can realize how important that understanding of the language is to be able to communicate. So as it was mentioned in the introduction by Dr. Vishnu, the internet's reach has become really widespread now. And then, there are so many people who are coming to the digital media. There are so many services that are launched, and people access those services, either through their mobiles or visiting the portals through laptops or computers. There are so many offices, even if somebody is not directly accessing those services through the dedicated apps or website, there are often different setup where people approach a kiosk or a desk, and they they fill up the required details, and then those things again get digitized and stored somewhere. And on this data are lots of different things, lots of different algorithms, lots of different services run. So here, although these kind of services, this kind of techniques work really well for some of the widely spoken languages in the world, the same is not true for many other languages. So there was a recent study that was conducted, and it was seen that there are more than 7,000 spoken languages in the world. Okay. More than 7,000. Now it's a huge number. Even I was really surprised when I heard this number, and if I have to recall the different language, or if I have to tell the different names of different languages that I'm aware of, it will be maybe 20, 30, definitely not more than 50. We're simply not aware of those languages. Forget about offering services in those languages. Then if we combine all those people, if we bring together all the people who are doing NLP research actively or developing services, if we again try to look at what are the languages that they are aware of, take the union of that, I'm very sure even then it will be very difficult to go to this number 7,000. Essentially, again, there was a study by Andres where it was mentioned that 95% of all languages in use today will never gain attraction online. What could be the reasons? Because maybe they're dying languages. Maybe those languages are not popular. Maybe those are spoken by a very small group of individuals in certain regions or locations. But even if we discount all these and say, okay, from these 7,000, can we have some applications which will work for say 200 languages? It's a huge ask. However, we all know that the world is now a global village, and if we want to take the benefits of NLP research to this entire globe, entire community, we need to look beyond some of the very specific, widely spoken languages. So here are some evidences uh, or some other additional information or statistics regarding where we stand in terms of language understanding, language resources, and so on. So the first plot that we see here is actually, so if you look at the y-axis here, it says the number of articles in Wikipedia. So for each different language, if we count and note down the number of articles which are there in Wikipedia, and then if we sort that list in decreasing order, we get such a plot. What we see from here, there are a few languages for which there are a huge number of articles. On the other hand, the moment we go say beyond 20 or 30, the curve is almost flat and aligning with 0. What does it mean? There are either very few or no articles on Wikipedia for these languages. And data from Wikipedia is actually a good source for training many algorithms. Also, it's some kind of indicator that how globally popular or how much different resources are there for each of these different languages. And however, if we talk about the most spoken languages in the world, this list, if we see, I think we are familiar, we are at least aware of the existence of all these languages. Then there was another study which was done by Pratik Joshi and his group. So this plot is a very nice plot, and it captures many information, many pieces of information together. Let us try to understand this plot. So here we see a few colored circles, okay, or parts of circles. So each of these colored circles is a grouping of languages. Okay, let us look at this group labeled as 5. So we see that this circle is actually very compact, very small, and this compactness of the circle or the size of the circle presents the number of languages in this class. So if we call it as class 5, so number of languages in this class 5 are very less. Okay. However, the y-axis is an indicator of the amount of label data that is available for this language across different tasks, and x-axis is the unlabeled data available for this. So for this group of languages, we have a large volume of labeled data as well as unlabeled data. And what does the color indicate? The color spectrum WebGeor represents the total speaker population size from low to high. Okay, represents the total speaker population size from low to high. Now R is at the end, and this ordering is from low to high. So this red circle has a huge number of speakers. So maybe that's why we have so many labeled data, we have so many unlabeled data. And NLP algorithms do quite well for this group of languages, and the same is true for languages from cluster 4, and I believe many of these languages will fall under the most spoken languages list of the world. On the other hand, if you look at 0 or 1, what do we see here? The circles are actually quite big, meaning there are many languages. Okay. However, although there might be a good amount of unlabeled data here, labeled data is very small. Here, very less labeled data, less unlabeled data also. On the other hand, if you look at the sizes of the circles, they are huge. That means there are a good number of languages here. Then this is G, which is in the middle of the spectrum, which means if we combine all these speakers, right, speakers of these languages, it's somewhere in the middle of the list. So there is a reasonable population that speaks this language. So there are so many languages, there are so many speakers, but there is not much data available for that. And maybe that is one reason why the NLP applications really didn't either become successful, or people didn't even try for these kinds of applications. So the question now is, what can we do to make sure that we are able to cover many of these languages? And if we are able to do it, that will be in some sense democratizing the benefits of NLP research. So with this, let us then try to understand, we talked about low resource a few times. What exactly is low resource? So it's a very common sense knowledge that to achieve good performance on a given task in a given language. So for example, classification task in some language, say Nepali language. What will we need? We'll need significant amount of data, because we know that the modern algorithms are quite data hungry. And yeah, that classical machine learning algorithms, maybe they could operate with a slightly lesser amount of data. But again, the fact is that we need some data to train those algorithms. And when we say data, since the algorithms are supervised in nature, most of these algorithms are supervised in nature, we need labeled data. And also, we need reliable tools. When we come to data, so if you take any task, so part of speech tagging, we need data specific to this task. Name entity recognition, data specific to this task. So the more number of tasks we want to address, the more volume of data we should be able to collect. And in some scenarios, there could be monolingual task-based data. And in some cases, we can also benefit from parallel data. So these points we'll touch upon slightly later again. And the tools that we talk about are mostly used for pre-processing, but they are very, very crucial. So for example, tokenizers. Tokenizers are at the very first step of processing these algorithms will be the processing this data will be the tokenizers. So we need very good tokenizers for this data, these different languages. There are needs for stemmers, morphological analyzers, so that we know, the root or the normal form for different words and so on. Now, except a few languages, getting good tokenizers, stemmers, analysis, morphological analysis, that is also very difficult and is an active area of research for many languages. Now, question is, we've already talked about the answers to these questions. Are adequate data and good tools always available? The answer is not always. And that's where the language can become low resource. Low resource languages, again, the way we are defining low resource language is that we don't have much data. And also language can be high resource like English, but the domain can be low resource. What does it mean? Suppose we talk about biomedical document, we talk about legal text. Again, the volume of data, volume of annotated data, those are there for these specified domains. Even that is very less. So to have good algorithms for these kind of that can target these kinds of domains, even that becomes very difficult with low data or less volume of data. So again, when we talk about low resource, there are different dimensions of low resource. So dimensions of of resource availability, whatever I cover in this slide and the next slide, that is mostly taken from this survey on recent approaches for low resource NLP. And this paper is also available online. One can look at that. So the first one is availability of task specific labels. If we have good number of task specific labels for a language, it's actually quite good and quite helpful. It's the most prominent dimension, but the thing is it needs human effort, which is time and cost intensive. And to generate this kind of data, one needs to be very familiar with the language and also the underlying domain or task. Then there is availability of unlabeled domain specific text or unlabeled language text. So many of the modern NLP algorithms, they work, they use embeddings. In fact, most of the, not many, it's actually the most of the modern algorithms, they are embedding based. Now, how are these embeddings obtained? So for example, we are saying that say English is a highly popular language. Okay. Now, for each of the tokens, like English is a highly popular language, each of these words are actually converted to an embedding or a vector, real valued vector. Now, these vectors are learned based on large volume of data, and their unlabeled data is actually used. So availability of unlabeled language can also help in developing good algorithms. Then there could be development of availability of auxiliary data in the form of knowledge bases, like tools like machine translation system. So we do not have data for a specific language, but we have a reasonable machine translation system. So maybe we can try to convert some of the high-level language examples from the high-level language to this low new language, or to this language, not new language, to this different language. So that we can do. So then there are different ways of doing data augmentation. Like how do we add new training instances? So say for headline generation is a task. Okay, headline generation in some language. Say it's some language is not spoken by many people, or for which which is spoken by quite a few people, so that publishing news articles in that language becomes helpful and also profitable if we can include that angle. And there are a lot many readers who are reading those news articles. So, and suppose somebody has written an article and we want to suggest a suitable headline for that. Then what may happen is that we have very few data examples for that. However, if we look at the examples, we are able to suppose we also have some very basic NLP tools for those, for example, named entity recognizer, okay? Or we have some ideas about the synonyms, words and their synonyms. What we can do is we can look at the input, we can replace some of the existing named entities with some named entities from a list. We can replace some words with their synonyms. And with this, we actually can create newer training examples. So we are able to increase the number of training examples here. Then it has also been observed in some research works that when we talk about a sentence and look at the structure tree, okay, the syntax tree of that, we can actually take a portion of that syntax tree, maybe one small subtree from that we can take. We can see which part of the sentence is reflected in that structure, and we can replace that structure by a new phrase or group of words, sentence fragment, and in the parse tree, only this subtree will change. Change will be local. So again, what it does is it gives us new additional examples, because getting human annotators to look at sentences and build a syntax tree is actually quite difficult, quite time consuming. However, here also we need linguistic or domain experts, linguistic experts or domain experts. So still, if we can assume the availability of them, then this actually is another way to increase the volume of available data for training. Then there are techniques for distance supervision, weak supervision. There are techniques for cross-lingual annotation projection. So many times these things rely on availability of machine translation system or parallel data. So what it means is that suppose you have a task for which you have an input and an output. Okay. Now, for doing this task on a high resource language like English or Spanish or French, you have a very good model. And also assume that you have parallel data. So in another low resource language, we have the same input, but the output is not available. For example, if we take the examples of headline generation or name entity recognition or things like post tagging and so on. So we have a very good model on high resource language. You have input output for high resource language, and we also have the input in the high resource language and in low resource language. So whatever the model predicts for the input in high resource language, so that prediction is then projected to the low resource language example. So in this way also, one can create data sets for low resource languages. And these are some ways in which the number of input examples or the size of training data that can be increased. Then modern NLP relies a lot on pre-trained language representations. So as we mentioned a few minutes back maybe, that for each token there is an embedding. But how do we learn these embeddings? So essentially these embeddings are learned to ensure that they represent the nuances or they represent the actual meaning, semantics that the word is having in the context of the sentence or paragraph where this is uttered. So large training data is required for getting this. So as long as we are able to ensure that for the low resource languages, we have large volume of unlabeled data, even we can have many pre-trained language representations which are helpful for this. So many times they use self-supervision only. So sometimes masking, sometimes denoising, sometimes order recursive kind of objective. So they have. Now, one thing that many people are now criticizing, or if not criticizing, they are marking it as a drawback or limitation of this, is the hardware requirement. Now, to be able to learn good representations for the different words or tokens, the underlying architectures are quite complex, and they are also, say for example, they may involve billions of parameters. Okay, and then for low resource language, if somebody is interested in developing an application or is getting started or evaluating certain approaches, then it becomes a little prohibitive to have such kind of very big architectures. Because hardware requirement might be a concern. There's a lot of load on the compute also. And then the last point, this was there from a paper, this paper, which came in like 2020, where the author showed that embeddings trained on smaller but curated low resource language sources are better. So what does it mean? So suppose we want to learn the embeddings, word embeddings for a language, one can take Wikipedia articles to train the embeddings. Now, what these people said is that there are certain languages where the way we speak, the way we write, or the way the native speakers speak, and the way in which those things are written in different media, there is a big difference. So sometimes there are different forms of the word. So for example, on top of O, there are a couple of dots. Okay, on A there is one dot that becomes a different character. However, when people write these things, many times they ignore those parts. Also, when people who are exposed to many different languages, when they write things, often there are presence of tokens from those other languages, code mixed kind of setup. Even in Wikipedia, many people say that those kinds of things are there. So in the work, these people, Labi and his group, what they did is they wanted to restrict the input so that the input articles that they have truly reflect the way people speak. And here in these languages, again, they showed that there are many words which have lots of different meanings. So again, when these things are very difficult to capture, so again, they said that when we have focused collection which come from people who natively speak the languages, or there is some way to establish the quality of how the language is represented in this collection. On that, if you learn the embeddings, the representation, they are actually better and more effective. So again, so there are different dimensions of resource availability, and fortunately, there are quite a few good paradigms which have come up, like this pre-trained language representations that has come as a blessing, so that one can transfer the knowledge learned from high resource languages to low resource languages in quick time. So many other things which would not have been possible are now becoming possible because of this kind of paradigm. But still, there is a lot of improvements that are expected. There are lots of drawbacks that need to be addressed. There are lots of concerns that need to be addressed. So here, so far in this presentation, we have talked about the data part. Okay? So how much data is available, how are we able to make use of it to generate more data, or with the same data, uh, are there some ways in which we can enhance the performances of the underlying algorithms. Now, let us look at a very specific sub-theme of natural language processing, which is natural language generation. Now, again, natural language generation kind of problems are very resource intensive, but they have become popular and they actually have a lot of, many of the modern NLP problems which are directly at the application level, many of these problems are actually natural language generation problems. So if you look at name entity recognitions, part of speech tagging, or identifying the structure tree, say the parse tree of a language, or the dependency tree of a language, those are somewhere in the middle level application. So there are typically the end users, they don't bother to know about the part of speeches, or people who use the services, they don't bother to know the part of speeches or the named entities or the structure tree and so on. There are some words Say, for example, if we talk about dialogue system, the user is saying something, the system is automatically responding with some relevant answer. Okay? Or somebody is at a place where the language which is spoken. So suppose this person goes to a supermarket and finds that the name of the product, the ingredients, the price, all those are written in some language that he is not familiar with, he or she is not familiar with. Then the person may make use of a machine translation system, so which can take input in that language and transfer it or translate it into this person's language. So again, this is directly at the application level that the user is interested in, right? So natural language generation has become a very active area of research, and it is one of the most challenging types of applications. So for example, most of these things are one-to-many, and we have a combinatorial exploding out to space. In the next slide, we'll have some more examples of this. The question is how to deal with low resource languages in such challenging setup. So here are some examples of NLG tasks like human-to-human communication. So I am speaking in English, but somebody at some other part of the world is listening or is subscribed to the stream, getting the presentation may be automatically converted in his or her own language. That becomes useful. So that's an example of machine translation. Then human to computer communication. So it could be like dialogue generation, the example that I gave. There are some other kinds of systems like question answering, distractor generators, and so on. Distractors are like in many reading comprehension examples, we have multiple choice questions, right? So there's a passage, there is a question, and then there are some answers, a few possible answers, and one has to select the correct answer. Now, typically only one answer is correct, and then there are some answers which are incorrect. So these incorrect answers are distractors. They are designed to distract the user or the test taker from the correct answer. So can we generate distractors automatically? So it's again some example of human to human computer communication. Then there could be something like computer communication. So suppose there is a code, okay, program, and can we have a natural language explanation of the code? Or suppose somebody has written a program in Python and it needs to be converted in Java. So in all these cases, what we see is that input is a sequence of words or sequence of tokens, and output is also a sequence. Machine translation, output is a sequence. Dialogue generation, output is a sequence of words. Similarly, natural language to code, output is a sequence of words. Now, the same thing, for the same input, the output, there are many different possible outputs, right? So if we talk about machine translation, the same thing can be seen in many different ways. So although the input, there's only one single input, the output can be many. So these systems are actually one-to-many. And the moment we talk about this kind of languages, right? So the output can have any number of tokens. It can be 1 word, 2 word, 10 word, 20 word, 500 word, and so on, depending on the underlying task. And then there are so many different permutations possible of different words that are feasible and could respond. So the output space is actually also huge. And that's when these problems become even more challenging for low resource languages. Right? So now suppose we have one such application, say headline generation. Now we have data in English language. So input is in English, and this system, what it will do, It will take that input and generate the output headline. Now we have good amount of data. We are able to train a model, and we are able to have one algorithm for this. Now suppose we want to enable this service for other languages also, maybe some other language L1. Then what do we expect? Again, input output pairs, architecture, training, and model. Language 2, again the same thing. Now the moment we want to plug in more and more languages, this thing needs to be redone again and again. So multiple problems. The first problem is that getting this input output pairs. Second problem is that training and deployment, again a headache. Third problem is that maintaining all these different models. Okay, periodic retraining, flushing out of old models, bringing in new models, storage capacity, understanding the input language, and then selecting a language, selecting a model. All these become problematic. The question is, can we train in one language and test on other languages? So we have one single model. Maybe for English, we have good amount of training data, so we train it on English only. But when some other language input comes here, okay, maybe Arabic, this model should be able to generate the output in Arabic. One single model, can it be able to do it? When, again, it is not exposed to any data, or it is exposed to very less amount of data in these other languages. So that's where we try to develop a framework which we call as ZEmbed, which is unsupervised cross-lingual transfer framework for language generation. So it's from ACL 2021 findings. Okay, the next part of the, or next few slides actually talk about this framework, where we try to show that we are tackling low resource languages, but if we have a suitable framework, it might be easy to plug in more and more languages. So this work, I'm skipping the literature review part. In most of the cases, either people use parallel data, and we know that getting parallel data is very difficult. And then some of them are based on machine translation pipeline, like back translation. What they do is say, suppose I want in some language, a Japanese language. So my input is in Japanese language. I translate it to English language, and then I pass it to English generation model. And that model gives me an output in English. I convert it back to Japanese. Okay? So back translation. So many people use this, but again, for the languages which have low resource, which have low resource availability, for them, even this kind of translation systems are not very good. So machine translation systems also need to be trained, right? So if not much data is available, not much corresponding parallel data is available, this training also can be weak. So especially for low resource languages, this becomes even more problematic because they introduce many noises. Okay? And as I again said, many of these algorithms or techniques are actually targeting a problem which is at the application level only. So whatever result is produced, the user directly consume it, like response from a conversational system, a summarization system. So there, these small these errors in the translation system that make the user experience very, very poor. So yeah, empty systems are not perfect. So generated texts are error prone, and these models are not scalable to low resource languages. So there are many other approaches on parallel data. So what we wanted to do is we want to develop a framework that can generate natural language text. It does not require parallel data, does not rely on back translation mechanism, and it handles different generation tasks in different languages, and does not need task-specific supervised data for different languages. So in typical literature now, it is called a zero-shot setup. And if only few examples are available, then yes, that can become a few-shot setup. And typically, few-shot performance is better than zero-shot performance. So our model is called as ZEmbed. So we used mbert as the basic architecture for this. So we have an NLG model. Okay, so it can generate natural language text. It does not require parallel data. We use monolingual data only. Okay, so what does monolingual data mean? So some text fragments written in the languages under consideration. Okay, not supervised. It can be newspaper article. It can be a note which is prepared by a student. It can be some dialogue which exists somewhere, some movie or whatever. So the data has to be in that language. That's it. And then we use an unsupervised auxiliary task so that the latent spaces of the different languages get more and more aligned. So that will help us in avoiding the requirement of back translation. And we actually test with 4 tasks and 3 languages in zero shot and few shot setups. So what are the examples? Zero shot and few shot. Number of examples can be 0 or a few. The task can be question generation, destructive generation, summarization, and headline generation. These are the 4 tasks that we tried with, and 3 different languages which come from 3 different language families, language categories. Those are there. So little detail about the algorithm, because we propose it as a framework, and different tasks, different languages can actually be plugged into it. So it's an encoder-decoder architecture for language generation. So we'll give a very brief overview of encoder-decoder architecture. So we start with pre-initialized embeddings which come from Embed. These are multilingual embeddings. So the languages that we cover, so those are covered by Embed also. So there is some warm start which is provided by this. So some initial representations of the words are available from Embed. But Embed representations may not be suitable. The reasons are there in the next slide. So we involve something like an auxiliary task to further pre-train the embedding. So this is about Embed. So what it does is, suppose this is for an English sentence. So there is a sentence that was there at input, and this model will mask some of the existing words from this. Okay, and it may also shuffle the sentence ordering. So in some sense, it is corrupting the input. Now this corrupted input goes into the transformer encoder. The encoder final state gives some representation of the input. That representation comes at the decoder, and decoder, based on that, starts emitting the words one by one. So essentially, we expect that the output will be the true version of this corrupted version. Okay. So the objective is mostly masking and denoising. So we want to identify the words in the mask, and if the sentence order got permuted, we need to get that. So again, it was trained on multiple languages, I guess 25 languages. And through this, if the model is able to predict the words correctly, identify the sentence ordering, all that, we can expect that the model has learned something about the word. Now, this knowledge, which is embedded in these parameters of the encoder and decoder, they provide, the initial thrust or momentum or warm start when we take this learned architecture and apply it for some other task, because it has learned the language, we can say. However, the objective here is mostly masking and denoising, but in case of natural language generation, say, mostly the output is auto-regressive in order. So one by one, the tokens are output. So that's in auto-regressive setup. What I am predicting, what I am producing next, what token I am producing next, depends on what I have produced in the past. So it's conditioned on that. So it's an auto-regressive, but this one is not auto-regressive. And also, if we directly take this and apply on some other task, so here they're seen all different languages, right? All different tokens from all different languages. So many times, although my input is in some specific language, say for example Bengali, in the output we see tokens from many different languages are coming. So code mixed output is coming. So again, which is not good. So we wanted to do something on top of this training so that these problems go away. So that's why we add an auxiliary task, which is further pre-training of Embed. So this part we have seen why we need that further fine-tuning. So that additional task or auxiliary task that will be plugged in on top of this Embed training in this framework. So it should only utilize monolingual data. Again, we are very much aware, and we are very much certain that we do not want to involve any parallel data or background data. We want monolingual data, and the decoder training will be in auto-regressive. So the task needs to be auto-regressive, and it should enrich the Embed latent representation about selected languages. So we define this as the task. So given an input passage, generate few random sentences from the passage. So this task is not a very, what should I say, an elite task, not a very meaningful task. But this is a very simple task, And we are able to show that with this kind of simple tasks only, we are able to get some better alignment of the representations of the words, the embedding. And many of the problems with code mix generation, those things go away. So given an input passage, generate few random sentences, which we call as random summary. So to make the data to train this auxiliary task, we need passage and corresponding summary, right? So those will be the input examples. So how do we generate a passage? So we assume that for each language, we have been able to get a collection of monolingual data, maybe some passages for each of these languages. So we generate a random number I, which is the starting point of the passage. We generate a random number k, which denotes the size of the passage. Okay. Suppose this is 3 and k is 20. So from 3 to 22, these many sentences we take up, and that becomes a passage. And what's the summary? Okay, yeah, so we have concatenated all those. We get the passage, and then randomly we take 20% sentences from here, and that gives us the summary. And this passage summary thing becomes an input example for this auxiliary task. Again, done in a very crude way, but the impact is non-significant. Impact is significant. So repeat this n times, so we get a data set. So this is something that the pre-trained embed gives. Now further we are pre-training with the auxiliary task. At the end of this, the latent space is better organized. So different, so we can expect that, okay, words which are synonyms across different languages, so they come together or close by in the embedding space. Words which are that are functionally similar, even if they are not synonyms, even they could share some space, same space in the latent space. And with that, we can now do task-specific fine-tuning on English supervised data. So again, assumption is that for English, we have good quality, good volume data. And once we have trained that, we do zero-shot evaluation or few-shot evaluation of the other language data. So this is what we do. There are some problems like catastrophic forgetting, which is common for this kind of tasks. So fine-tuned model only generates the text in English because in this part, task-specific fine-tuning, it was generating only English. So when we feed some other languages, it has somehow memorized and understood that, okay, I have to generate in English. So that we wanted to avoid. So one solution for that is decoder freezing. The parameters of the decoder, those were frozen during this. Then there was one more problem of spurious correlation that led to code mixing. And here also, data augmentation kind of techniques we applied to get rid of that. Now, with addition of these tricks, after addition of this very carefully and strategically designed auxiliary task, this model is now good enough to do target language generation for low resource languages as well. So these are the 4 different tasks that we tried out, and 3 different languages, English, Hindi, and Japanese. So headline generation, input is a news article, output is a headline. Passage question answering is that there is a passage and there is a question generation, there is a passage, and the answer is given. We have to generate a question. Then abstractive text summarization. So given a passage, we want to have a summary, and these summaries are not simply picked sentences. So different sentences can be combined, sentence can be split, the same thing can be written in a different way, and like that. So that's abstractive text summarization. Then distracted generation. I talked about that some time back. And we'll directly go to the evaluations, and what we saw is that this is actually doing good for all the different tasks across the different languages. So this result is for English, and depending on the task, the evaluation metrics are chosen, like Roge metric or bird score metric or blue score metric, and so on. So this is ZMBERT, which does better than others. And then this is for zero shot. If we have few shot, 1000 supervised data points, and if we are able to train the framework along with language specific data as well, and there is a huge jump. again, as expected. So these were promising. We tried it for, this is for Japanese language, and there also we see similar things. We did human evaluation. There also we had something which are very promising. Some example model output. So this is for headline generation. So this was the input, and the English version is given. So I'm just rushing now because I think we are close to 1 hour. So the headline, if this is the headline generated in Hindi, the same thing if we directly translate in English would be like, so this is about an incident, unfortunate incident which happened a few years back, where there was an army vehicle which was attacked, or army platoon that was attacked by terrorists, and yeah, few soldiers were killed, and then there was a response, and the terrorists were also killed. So with that, for that article, the ground truth headline is Encounter in Pulwama. That's the name of the place in Kashmir. Encounter in Pulwama, Kashmir, a terrorist killed. It was the ground truth sentence. And then the generated sentence was a terrorist killed in ongoing encounter in Pulwama. Okay. Capture the same thing. One additional angle has come in here, ongoing. And it captures the exact same thing very nicely. There are many other examples. This was again one example where there was a flood situation in Britain, in England, and then 30,000 people were evacuated from there. So here the answer given was 30,000, and the model has to predict the sentence that can give this, for which this is a correct answer. So here also the question, human generated question was that due to flood, how many people were evacuated? So the model generated thing was like, how many people needed to be evacuated during the flood? Again, these were based on zero shot. So this is actually quite encouraging. We have some other examples from other tasks. So it's an unsupervised framework for cross-lingual transfer and generation. So I'll briefly touch upon for the next 2 minutes or so about one more work that was a follow-up to this. So here what we realize is that the design of the auxiliary task, it's quite helpful, but can we get rid of that also? The second thing was that here we could target 3 languages, but suppose we want to expand to 30 languages. How do we do? Then there is something called language typology. So there are different origins of different languages. There are some languages which are similar between themselves than to others. So these kind of things, this kind of linguistic knowledge, can we bring in some framework? So the next work is called Meta XNLG, which appeared in findings of ACL 2022. It's a meta-learning approach based on language clustering for zero-shot cross-lingual transfer and generation. Okay, so here we use meta-learning. I'll give a very brief overview of the architecture. So we have different languages. So in this work, I guess we targeted 30 languages, and then we cluster the languages. How do we cluster? So we know that for clustering of objects, we need some feature representation and so on. So there are some repositories which give this kind of feature representations for languages. So languages vary from each other depending on the, say, subject, object, verb, their ordering. So how active, passive, voice, those things come into picture. So negations, how those are handled. So similarly, there is a framework called WALS, or World Atlas for Linguistic or Languages. So there, for each language, those kinds of features are identified, and the feature values are coded. Now, based on that, people try to learn embeddings for different languages. So English has an embedding, Spanish language has an embedding for itself, Punjabi language has an embedding for itself, and so on. Now, based on these embeddings, we cluster the languages using hierarchical clustering. So we used hierarchical clustering because we don't have to specify the number of clusters while feeding the data. Now, once we have the output, we can pick the number of clusters as we wish. So we cluster the languages, and for each cluster, we also identify the centroid languages. So suppose this is cluster 1, cluster 2, cluster 3, and green is the centroid language, and orange is the non-centroid language. So in this meta-learning part, initially we train with the centroid languages only, Okay? And after that, we test on the non-centered languages also. So we'll go to the results directly. Yeah, so there are some objectives regarding how many clusters to choose and so on. So, okay, I guess the transition is okay. Yeah, so these are the language clusters, and centroid is simple distance based centroid. So we had 3 clusters, 1, 2, and 3. Cluster 1 had say Hindi, Telugu, and Finnish languages. Cluster 2 has Spanish, Italian, I think this is Portuguese, this is French, English. Cluster 3 had Russian, Vietnamese, Thai, and these languages. So I'll go to the results directly. So the algorithm is like this, the typical machine learning algorithm, the same framework. And yeah, so 2 tasks of question generation and text summarization, 5 datasets, 30 languages, and 5 different evaluation metrics, human evaluation as well as automated evaluation. And there we saw that this model is actually able to do well across languages and across tasks. So with this, I believe it would be good to conclude, and if there are any questions, I can take that up. Yeah, so this was some example of how many clusters to choose, what should be the training languages, and so on. And this is actually a novel framework where meta-learning and language clustering for effective cross-lingual transfer. Meta-learning for zero-shot cross-lingual transfer, this was not studied, and this was the first time we did it. And yeah, coverage of 30 languages gives us some hope that it can actually extend to many more languages as well. But we were not able to. I mean, this was a very voluminous evaluation. We're not able to. Yeah, so if you are able to have more time for evaluation and other things, even this can be expanded. So to sum up, we need to cater to the needs of different languages or different language speaking communities. We need to focus on tools, better data setup. But tool and data, those are not enough. We need to integrate or handle those tool and data in some efficient frameworks or algorithms. Sometimes it may require some language understanding. For example, the language clustering, the basis of that was some language understanding. The algorithm developer didn't have that language understanding, but the community had that understanding. They have shared it in some format, and that could be useful. So even having these kinds of resources where one specific group of researchers can take help of that resources for the downstream task, even that could be quite helpful. So appropriate paradigm needs to be followed, keeping in view the low resource, zero shot or few shot scenario. So with this, let me thank all the people who are listening to it, and thank you very much.
Thank you, Dr. Manendra. That was really very insightful and very valuable work that you're doing.
Thank you.
So any questions from the participants? I don't see any questions on YouTube. There are a couple of likes, but no questions. Any questions on Zoom? Okay, in the meantime, let me ask you a question myself. So one thing that is different about some of these languages is the very concept of word, right? We have, like in the Indian languages, we have what is called a sandhi. So we join words together to make a new word. So is there any special consideration that applies to such languages?
Okay, that's a very good question. So the tokenizers, people are now designing language specific tokenizers.
Yeah.
So it can be handled at the tokenizer level. Many people are now trying to, actually a lot of research has now started on Sanskrit language, where these kind of things are more prominent. And people are also trying to see, how that can be used as an interlingua based approach. So whatever language we have, we try to look at, convert to Sanskrit and from Sanskrit to other language. So these kind of approaches are being looked at. But if anything specific about Sandhi and other things needs to be dealt with, it is handled at the tokenization part. Sometimes what people say is that when we do Sandhi, and if we look at the words, the final words that we get, often there's some pattern in that. Say, for example, the second part that is there in Sandhi, if that is same and the first part is changing, then the form of the generated or the Sandhi output will also change, but the latter part will be quite similar, right? So at the tokenization level, people are now working with subword tokenizers. So the tokenization will not give us the complete word, but even in the word, if there are some subwords, it is able to predict it. It's finally chopping the words also. So many times, although the Sandhi is not directly respected, but these kind of patterns, and based on that, the subword tokens are getting extracted. So people have seen actually that is quite useful as well.
Okay, so most of the language specific stuff seems to be handled at the tokenization level itself, right?
Right, right. And
Okay.
language specific tokenizer can actually, yeah, take into account the different things like Sandhi inside the tokenization process itself. But not much work is there.
Yeah, so are there any tokenizers already available which can handle these idiosyncrasies like sandhis and things like that?
Yeah, this I have to check. This I have to check. Yeah. So when the task is more at the higher level, okay. So whether we understand the words that got joined to give one specific word, whether that level of understanding and how well it correlates with the final output, right? Finally, if the output, if the target is say dialogue generation or summarization, then having a better knowledge of Sandhi or in the tokenization process, whether that is helpful or not very sure, possibly not that much. However, if you look at the lower level tasks of part of switch tagging, named recognition, so there these kind of things could be helpful. And good tokenizer can actually help there. I need to see whether there are techniques which handle this already. I guess the chances will be very less.
And the attention mechanism also is different, right? In the for the languages. So is there anything special that we need to do for the attention mechanism in like your BART, MBART and ZMBART that you're proposing? Is there anything different?
No, the attention mechanism does not change. So only thing that changes, so the encoder decoder framework, that pipeline, that remains the same. So sometimes we may change the input, and once we are able to see the input, tokenize it appropriately, get the embeddings, that from that point itself, the encoder decoder model starts working. So sometimes, suppose we want to give some additional indication to the model that, okay, your input language is this. Now, suppose somebody may want that, okay, the input is in English, the output should be in Telugu. So these things need to be passed on to the model somehow. So then they add some additional tags. So they modify the input in some way. So either language specific tag or some other indicator, task specific. Now, once they do it, the model architecture remains the same and it is able to handle the task. So the model architecture does not have anything which is language specific.
Oh, okay. I think we are over the hour and I don't see any questions on the chat window or on YouTube yet.
Okay.
So I will probably thank you for a wonderful presentation. I'll just share my screen for a while to present you with this certificate. I hope you are able to see the screen.
Okay, I have to stop my sharing, right?
Yeah.
Okay, 1 second. Yeah, I can see that. Thank you very much.
Yeah, if it was live, we could have presented a plaque and things like that. But in the absence of a live event, this is what I thought would be appropriate.
Yeah, thanks a lot. Yeah,
Yeah,
very nice.
thanks for the presentation again. And just a note for the viewers that we have more events coming up. Next month's event is on quantum paradigm for machine learning by Professor Amlan Chakrabarti from University of Calcutta. It's on the 2nd of January at 8:30 p.m. Pacific time. So please feel free to attend. With that, I thank everyone who's attending the talk on YouTube and on Zoom. And thanks again, Dr. Maunendra, for taking time out from your busy schedule and really for a very insightful talk.
Thank you. My pleasure.
Yeah.
Okay. Bye, everyone. Thank you.